Hello, my name is Steven. Welcome to Highfinder Tech Talks. Today, we are going to talk about pressure regulators to Jack Samways, who works at Pressure Tech, and he's very passionate about this. He has two degrees, one in mechanical engineering and one in renewable energies. And he's connected to us directly from the factory where they actually make those. So thanks very much, Jack, for finding the time to do this. And welcome.
Thank you very much. No worries. Glad to be here. Hopefully shed some light on our experience of pressure regulators and the industry that we're working in.
Yes.
Thanks for having me today, Steve.
Absolutely. So Jack, just as an intro, can you tell us what is exactly a pressure regulator and how does it even work?
Of course. So a pressure regulator is a mechanical valve that would take a high pressure to a small pressure in layman terms. So how it works is you have different types of regulators. You have both spring-loaded and air-loaded. Spring-loaded works like a manual valve. So you turn a valve, turn this handle here, and it pushes down on the main valve. And so you'd have for example, you'll have a 350 bar stored on the inlet,
yes,
and the outlet could be 10 bar.
Yes.
And the main valve, as you turn this handle, it builds up the pressure on the outlet. So this application is most especially used in fuel cells. Fuel cells have a required flow rate, have a required set pressure, and you use our regulator to achieve this required flow rate, to achieve the required set pressure.
Okay, so when you say flow rate and pressure, so can you say a little bit more again, what's the difference there for those who are still looking for orientation?
So a fuel cell, so any fuel cell manufacturer, once you implement it into a hydrogen system, so for example, a hydrogen fuel cell truck or bus, you have a fuel cell with a power rating, and that power rating defines a flow rate. So how much kilograms per hour or grams per second off that hydrogen you're getting from the cylinder source to the fuel cell. It has a requirement. And what varies in some of the regulator is if that flow rate requires to be higher, then you have a larger orifice size within the side of it inside the regulator to allow more flow to come through. Alongside that, they also have a required set pressure. So it's the pressure of hydrogen that's coming through to this fuel cell, also a requirement for that. And one of the key things of why our regulators are important for the system is because the accuracy is very defined for a fuel cell. So you can't vary too much in terms of the flow requirements, the set pressure. They have to be very specific. And that's why it's very important in terms of the design of the regulator to ensure that you're getting this accurate flow, accurate set pressure.
Okay, thank you. Well, so given all these specifications, can you shed some more light? Can you take us deep? How does like the inside works of, for example, that device? How would that look? How does that even function?
Well, perhaps I can show this video.
Yes.
If you're able to.
Oh yeah, we see your screen. Yes, we see that.
Can you see the video?
Yes.
So as you can see from the right, that blue dotted line that's coming.
Yes.
So that's, for example, 350 bar pressure that's coming through our pressure regulator, and the red flow coming out, that's the perhaps 10 bar that's coming out, and that will be going to the fuel cell. So as you can see, I showed this regulator before about how this hand wheel, it turns.
Yes.
And as this hand wheel turns, it pushes that valve just in the center. You can see that valve oscillating up and down.
Yes.
So as you push that valve down, that then allows that 10 bar to come through from that red line on the outlet. So that's the kind of the basic kind of flow characteristics you'll see coming through the regulator, and that's what allows you to achieve the required set pressure.
So
and then
so that means that movement we see going up and down is essentially somebody opening and closing, and that changing.
Correct.
So it's a very fast way. Okay, it doesn't oscillate like that during operation. That's
no,
just
certainly no. So what we'd normally have in this sort of application is almost like a set and forget regulator.
Yeah.
So you turn the regulator to the required set pressure, and then you'd leave it. And so this regulator can be used again and again with that spring at that constant. So when that main valve goes down, that will stay stable.
Yes.
With that required set pressure coming out.
Yeah.
And then the valve will be depleted, and then it'll be refueled and then depleted. So the spring will stay as compressed throughout operation.
Yes.
But all that would change is that blue line. So that that pressure will become high pressure, then low pressure, high pressure, then low pressure.
Yes, understood. Okay, so that means the spring is the one that does all the regulating.
Exactly, yeah, and that's how a manual pressure regulator works.
Okay, those are manual? Are there any other ones?
Manual, yeah. So also, which I can go over at a later time, we also have air-loaded pressure regulators, which offers automated control. So that's when you use like a PLC and the regulator communicates with the computer to automatically change the required set pressure depending on certain applications to do mainly with hydrogen refueling.
Okay, so that means, so in that case, I could, from a controller device, say I need this and this output pressure, and then it will basically vary to give me exactly that pressure.
Yeah, so it's more in terms of an example. So when you're refueling a vehicle of some sorts, you have a ramp rate. So there's a corridor you have to stay within.
Yeah.
And if you notice that if the IP controller, so the controller that's controlling the pressure regulator, notices that it's overpressurizing, overheating, they'll vary the pressure, which will bring down the heat, bring down the pressure to ensure that you're staying within this corridor. So it notices changes throughout the vehicle refueling, and it will react to that automatically without anyone having to touch anything. So it's not like this manual regulator that you're seeing here on the screen. That's someone turning it like themselves, but then they would leave that at that compressed spring to give that achieved set pressure. But then on a different application, it would be automatic, so it's hands-free.
Mm-hmm. So that means that on the manual, it will just set to whatever, let's say 12 bar or 6 bar, and just give me that all the time. And then,
correct.
But Jack, I need to ask you one more thing, because I've been wondering this myself. So if you set a pressure regulator to 6 bar, and then you have an input pressure, maybe at some point, maybe 30 bar, and then the input pressure goes up to, say, 100 bar and drops down again. How is that on the output side? Is it the same all the time?
So it's a good question. So one thing that as designers of pressure regulators we have to overcome is a phenomenon called the decaying inlet effect. So you often see in most fuel cell and ICE applications, the generic characteristics of the application is that you'll have a stored high pressure, and this will be reduced as the fuel cells consuming this hydrogen. So one thing that
as the tank gets emptier, sort of.
Exactly, yes. So as the tank reduces, and the vehicle's being driven and therefore using the hydrogen, consuming the hydrogen. So one thing that happens to the inherent nature of pressure regulators is that something called the decaying inlet effect. So you will see an increase in the set pressure, so the downstream pressure, as the inlet pressure is being reduced.
Yes.
So one thing we do to overcome this is either use a two-stage solution, or in terms of what we've designed, and which is a really key characteristic of the regulators, is a balanced main valve. Mm-hmm. So what a balanced main valve does is it shares the load of the force that's overcoming the spring to give you the set pressure, and it enables a really stable set pressure, which works like a two-stage. But in some applications, such as, so for the 350 bar system, you can utilize a 350 bar, a balanced main valve spring. Alternatively, for the higher pressure, so for 700 bar, when that's depleting right down to about 30 bar, you would need a two-stage solution. So our new design for the Auto 875, which is the higher pressure for 700 bar cylinders, would utilize a two-stage solution, because this has two springs on top of each other. So it's like a step down. Okay. So you bring like 700 bar down to 50 bar, and 50 bar down to your required set pressure. So maintain more stable set pressure.
So essentially what you're saying, okay, by the use of two springs, you overcome the possible variance. So even when it goes from 30 to say 100 bar, you can still have that. You can still have the same 6 bar coming out on the other side.
So this would be the Auto 438 for 350 bar cylinders.
Yes.
And a 875 would have another leather spring on top of this. So it steps it down in 2 steps, and that maintains on this really high pressure, maintains that stable outlet pressure.
Okay, that's interesting. So just in terms of numbers, and then I'll stop. If you have, say, let me say you want a 6 bar output, and your input varies from say 20 to say 60 bar, would that 6 bar, would that go up to 6.1 or 6.5 or 6? Would we notice at all this difference on the other side? Would we notice?
I think under like a 40 bar depletion,
Yeah.
you wouldn't notice it. It's more under like hundreds of bar where you would notice a slight increase in set pressures, and this is inherent across all pressure regulators.
Yeah. Okay.
So that's why one of the challenges that you have to combat is when there's really high pressure, really high storage pressure is being depleted right down to its minimum pressure for the cylinder. So it's more like 350, 500, 700 bar. That's being dropped right down to about 30 bar, okay, where you'd have to implement these changes, such as a balanced main valve or a two-stage solution.
Okay, understood. So maybe just looking around, as you mentioned, there's across various applications. Can you tell us where are pressure regulators actually found in the hydrogen economy? Where would we find them?
I don't know if you can see the slide.
Yes.
Excellent. So as Pressure Tech, when we first began kind of exploring the hydrogen industry, we wanted to cover as much as the hydrogen ecosystem as possible. So on the left, in terms of supplying hydrogen, electrolyzers are the key kind of source of producing hydrogen from water nowadays, because you can use surplus renewable energy to produce this. Once within an electrolysis machine, you use a back pressure regulator to control the hydrogen being produced. Alongside this, we have the RF1034, so the dispenser side regulator. So for refueling stations, you require a pressure regulator to bring the stored 950 bar down to about 350 or 700 bar, depending on what you're refueling. So alongside that, you have a range of regulators that are used in both fuel cell and ICE engines. So that's our range covering drones, buses, trucks, then soon to be passenger vehicles too, forklift trucks and other kind of lightweight hydrogen applications. So that's kind of the main kind of like our main range of hydrogen regulators. And perhaps I can go into a bit more detail.
Yes, please.
So I touched on electrolyzers. So that's kind of the key in terms of what's getting investment at the moment, and where there's a lot of companies doing a lot of work in this industry. So electrolyzers, you put an electric current through water.
Yes.
And what's produced is both splits H2O into hydrogen and oxygen. So these are both then stored. These gases are stored.
And where would you need a pressure regulator there? I mean,
that's right. So downstream of electrolyzers,
yes. So the electrolyzer produces hydrogen at
exactly, yeah. So you have water, you electrify water, and this splits the water from H2O to hydrogen and oxygen.
Yes.
So you need regulators of both sides, both lines of hydrogen and oxygen that are being produced. And often these electrolyzer companies implement back pressure regulators. So what I've discussed before is forward reducing pressure regulators, which control downstream pressure.
Yes.
What a back pressure regulator does, it controls upstream pressure. So it's when you require really fine control of a certain pressure, and usually in this case it's 35 bar.
Yeah.
So it works almost like a relief valve.
Okay.
So this is a back pressure regulator here. So you'd have the 35 coming in, and so any pressure above this 35 bar set pressure would get relieved off. So it's maintaining a really, really stable.
Okay. So that means you have the uniform pressure inside the reaction container. It just gets pulled off when. Okay. All right.
And it's good in terms of like what we have. We've been supplying back pressure regulators to various applications throughout our whole existence. So we have a wide range of regulators with different CV sizes. I mentioned about how flow rate influences the CV size of a regulator, which is the orifice size, so like how big the diameter is that's coming through. So as electrolyzers inevitably become bigger, as the demand for green hydrogen becomes greater and a larger power electrolyzer required, that then defines a larger flow rate and therefore CV size for these back pressure regulators that we supply in these applications.
Okay, cool. And any other areas where these regulators
by all means. So going on to, I mentioned refueling stations. So that's a key market for us, as we've got a lot of experience in kind of high pressure regulation. So as you can see, I've got one here. It's quite heavy to hold, so I can't hold onto it forever. So I mentioned about what you have here on top is this air-loaded actuator. So this works indifferent to the manual spring-operated regulator.
Can you say that this is the air-loaded actuator, you call it?
Air-loaded.
Air-loaded with air, okay.
Yeah. Okay. Exactly. So in terms of the design standards that influenced and helped us, create this pressure regulator, there's two main refueling standards. So there's the SAE J2601 design protocol. And this protocol, its main aim was to prevent overheating, overpressure of hydrogen cylinders. One thing you have to overcome when refueling hydrogen vehicles is the reverse Joule-Thomson effect. Also defines both pressure and the flow rate of this. So what you're seeing on that diagram just there is everything that's covered by this J2601 design standard. So the key thing for us is having a regulator that's responsive enough to stay within what we call the pressure corridor. So the diagram on the right that you see, that is the corridor where, as the regulator, so you start the vehicle maybe at a 30 bar. I mentioned when it's being right depleted, and you want to bring it up to 350 bar. This regulator is used to ramp up that pressure, and it's got to stay within that within this corridor. And so how it does this IP controller, so it's an electronic controller, it connects to the top of this air-loaded pressure regulator. And it communicates, it tracks both the pressure and the temperature of the refueling process. And if it ventures outside this pressure corridor, then it will alter the flow rate coming through the regulator to ensure that it's staying within this corridor. So it's like reactive as it's ramping up. Alongside this ISO 19880 standard. So this defines more the design of the actual valve. So it defines the strength. So as you can see, as I picked up, it's got a huge wall thickness. It's a heavy regulator. The strength values of this regulator stipulates that the regulator must take a pressure of 2.4 times the maximum working pressure, which works out to be 2,500 bar, which is incredibly high pressure. So we implement really high mechanical properties for the steel that we use, and it defines both the torque values on the ports and the leakage rate as well.
Why would it go that high? Sorry to interrupt you, but why would it go that high? I mean, with the cylinder or whatever storage, is there a risk that goes so high in terms of pressure?
It's not a risk. I think, which quite rightly, to be honest, as the industry developed, what we've lacked is these clear indications of the design standards that the valves and components that go into all hydrogen applications should adhere to, and they have developed as the years have gone by. So I think it's a huge safety factor. Like you wouldn't normally apply a safety factor this highly to a regulator for any other application other than hydrogen. But because of the inherent nature of regulator and the fact that you're storing at incredibly high pressure, there is not a risk, but it's just a safety element that people the industry requires. It's just one of those things. It's the ISO have defined it, and because they've defined it, we've designed it in accordance to that, because we want that stamp to say that, okay, well, we've adhered to all these standards to ensure that we're the market leaders, really.
I noticed in your overview there that you have, so we've talked about refueling now, and so that was it, or you also have them in vehicles?
So that's just kind of, as you can see, I know I picked it up, here's the regulator in a nice image there. So yeah, I can move on to vehicles. So I think so as you can see here, the Auto 438 fits on a hydrogen truck. So it fits upstream of the hydrogen cylinders and downstream of the cylinders and upstream of the fuel cells. So as you can see, the inlet pressure comes from the cylinders, which if we just play that video again, you'll be able to see.
And what was this? So this one goes obviously from the cylinders, which are operating at 350 or 700 bar. And what is the typical outlet pressure for this?
So this is like the kind of the chassis of a hydrogen truck. So as you can see, there's a bank of cylinders here. So they'll be stored at either 350 or 700 bar. And then you'll have a fuel cell. This that stack you can see just there, the grey stack. That's a fuel cell stack. And then you'd have our regulator in between. So as I mentioned, the inlet pressure would be this on these cylinders, either 350 or 700. And the fuel cell, it varies. On fuel cells, are usually around 10 bar. If it's an ICE engine, could be higher. ICE engines generically take a larger pressure for the engine. ICE engine being internal combustion engine.
Internal combustion. So what pressure ranges do they go?
The thing is, it varies from customer to customer.
Okay.
So there's no.
But it's not like 100 bar or.
It wouldn't be 100 by. It could be 50.
50. Okay. Okay. Cool.
But generically, most of the industry has gone towards fuel cells. But I'd say each customer, it varies completely.
Yeah,
There's no set industry standard of this is the set pressure you require for this fuel cell.
Okay.
It varies completely.
And yes, please.
Sorry, I was just to show you, like, this zoomed in, and this is the Auto 438 that fits in between these two. In terms of a simplified version of that, how it fits into the design. I think it's quite a clear image to show them how it integrates in.
So this is automotive then in the refueling, and that's it more or less, right? In terms of
one thing that's of note is the EC79. So it's the design standard that goes into place, what the regulator has to be certified to be supplied into this application.
Yes.
So EC79, which has now been repealed to like a new design standard. So we're talking about this, like, kind of all the design standards changing, but EC79 has been like the generic approval process to supply regulators and other applications, other components onto the market for vehicle applications. But throughout this, I mean, they undergo like 90,000 cycles, like equating to 10 years life cycle, salt spray, shell testing, performance testing, leaking testing. So it's very like a complex testing standard, but it's what's required to supply this on the industry. So it's just obviously what has to be carried out.
Okay, cool. So that's, wow. So that means these are all EC79 standardized. I guess we can do a separate video on the whole standardization topic.
Certainly could. You get like a certification video.
Exactly. But Jack, I must tell you, this has been very interesting. Unfortunately, that's about all the time that we got for today. But thank you very much for taking even the big one out from the shelf. And now we know what heavy work those guys are doing behind you in the production.
Behind me we've got our assembly team. So Pressure, we have our own CNC machine shop, and just behind me there'll be assembling the regulators, then pressure testing them. So a bit of an insight into the factory that goes into making these regulators just behind me.
Okay, cool. Well, thank you very much, Jack, for taking the time. This has been an absolute pleasure. So I thank you, and I thank the audience for watching. You can find components like these on HiFinder, and other components that you need to put systems in the hydrogen economy together. So please have a look there. If you like the video, please give us a like or follow the channel. In any case, thank you for watching, and feel free to watch any other video, and we hope this can bring you forward in building the hydrogen economy. Thank you very much.
Thank you. Cheers. Thanks for your time.
Bye.